Chem 30s, welcome back. We're going to go into something called spontaneity, and this is this is essentially the most important topic of the whole unit. If you can understand how spontaneity works now, you're going to make, honestly, the remaining of the unit significantly easier than the rest. So one thing we're going to do is quickly recap reducing agent and oxidizing agent, because it's often when people mix those up that they do this process wrong. Remember that reducing agent actually gets oxidized, right? So if you see the oxidation number increase, meaning become more positive, then you know that it's a reducing agent. Or if you're writing it the half reaction style, if you see the electrons on the product side, you're dealing with a reducing agent. Now, the oxidizing agent is going to be the opposite. It's going to get reduced. So you would see your oxidation number go down, or if you're dealing with the half reactions, you would see the electrons on the product's side. Sorry, I meant the reactant side, not the product side. And what we're really trying to say here is that when I have an oxidizing agent plus a reducing agent, what we get is a redox reaction. And here's one key thing to remember. Now, almost every single reaction, like any type of chemical reaction, whether it's combustion, decomposition, formation, single replacement, etc., is potentially a redox reaction, meaning there's usually something that is losing electrons and something that's gaining electrons inside that reaction, except for double replacement reactions. So every reaction that you've dealt with could be a redox reaction, except for double replacement reactions, and we'll show you why. So let's take this double replacement reaction, for example, over here. Now, the first thing that we would do is we would assign oxidation numbers to these. And when I assign oxidation numbers using all the rules, I get as follows. I'll do this rather quickly here. +1, -2, and then that's +1. This is -1 in brackets, -2. And then this would be +2. This is -1, +1. This is +1. I know that there's two of them, so I'll put a +2 in brackets. This is -2. And since there's two of them, it'll be -4. And then this gives us with +2 as well. Now, when you look at all the oxidation numbers individually, doesn't matter which one you look at, you see that none of them change. If I look at the copper, it's 2+ here and it's 2+ there. If I look at the chlorine, it's -1 here and -1 here. Remember, I'm not interested in the brackets. That's just the total. But what we're interested in is the charge per atom. If I look at the sodiums, they're all +1. And if I look at the oxygens, it's -2 as well. And so if there's no change in oxidation number, then what that means is that there's nothing really losing or gaining electrons. Therefore, there is no redox reaction. And I want to stress, this is for double replacement reactions only. Now, not all redox reactions work, meaning that when I mix things together, the reaction doesn't always work. Some reactions need extra energy, whether that's heat or electrical energy, or catalysts, etc., etc. Others are fine on their own. The reactions that don't need energy, so when I mix them and I don't have to heat them up or add electricity or add a catalyst, we call those spontaneous reactions. So what we're going to stop saying is that this reaction works or doesn't work. What we're going to start saying is that the reaction is spontaneous. And there's a set way that we can actually predetermine whether a reaction is going to be spontaneous or not. And so when a reaction doesn't work, we say that it is non-spontaneous. Now, the actual science behind this is quite a bit complicated. And what we're doing is we are mixing different types of energies and making the concepts behind those energies equal each other. For example, we are going to exchange a lot of electric potential energy to thermal energy. Now, since energy is conserved, we know that they are interchangeable. But the real idea of spontaneity, originally, you could say traces back to Gibbs's idea of free energy. And that's really how energy is exchanged from a system to the surroundings. And so one of the key words that we're going to just briefly mention, this isn't a university class, so we'll just leave it, here, is entropy, which is that a reaction will essentially happen when your molecules or your atoms go into chaos or disorder. And so the way you could think about this is kind of like a bookshelf. I want you to think about what would involve less energy or less work on your part. For you to take 1,000 books and put them on the shelf, or for you to tip a shelf over that has 1,000 books. And so you could think about, and I guess the obvious answer would be that it'd be a lot easier or a lot less time consuming to just tip the bookshelf over. Now the number of books don't change. Whether you tip the bookshelf over or you build the bookshelf back up, there's still 1,000 books all with the same total mass. Yet it would definitely be a lot less time consuming to just tip the shelf over, to make a mess rather than organize. Well, reactions work sort of the same way. So when we measure the entropy of the system, what we're really seeing is how easy is it for the system to descend into chaos. And if it can descend into chaos pretty easily, then it is going to be spontaneous, or what you're going to see is that the reaction works. And so the easier the system can go into chaos, the more spontaneous it's going to be, or the quicker, not even necessarily the quicker, but you could say the easier it is going to be to make that reaction happen. Now this process is quite complicated indeed, and in actuality we need to consider three things. The first is the electric potential difference, and that would be between the two reagents in a reaction. The other thing to consider, and it's as important, but we won't holistically consider it in Chem 30, is the temperature of the experiment. Certain experiments need to be done at certain temperatures. Some of them need cooler temperatures and some of them need warmer temperatures. And so although you might prove that when we're discussing electric potential differences in reaction, that they would tell us it's spontaneous, often without knowing the temperature that the experiment has to be conducted at, it still wouldn't work in real life. As well as the concentrations of the reactions. Now, of the reactants, sorry. What we're going to look at in Chem 30 exclusively is your electric potential difference. And we're going to use the redox table that is in our data booklet. Now, what you're going to do in your Chem 30 data booklets is that you're going to go to page 7 of your data booklet, and it should look like this. You should see a series of reactions that start with fluorine gas, right over here, and then go all the way down to your lithium ion over here. What we're going to look at here is a couple of things. First, we have what we call the reduction half reaction. And when we read anything on the left-hand side, okay, so this whole area, these are all reduction reactions. And we can see that because the electrods, no matter what one we're looking at, are always on the reactant side. Now, what I also want us to take a look at here, we'll write this in a different color, is you'll notice that, and let's expand this a little bit so we can see it a bit better. If you look at each half reaction, there's also a double arrow. Now back in Chem 20, that means that the reaction is reversed. And the same is true over here, but what it also tells us is that if you go backwards, meaning if I read from F minus to F2, or fluoride gas, then this is an oxidation reaction. So here's how, when we're paying attention and reading this chart, this is what we want to see. When we read this table from left to right, so going this way, okay, this is a reduction reaction, right? So reduction half reaction more specifically. Now, with the same understanding, and I'll write it over here, when we go from right to left, so we're going to read it, let's say I pick water here, we're going to go this way, then that's going to be an oxidation, I'll just write oxid, half reaction. And the good things about this as well, this whole table, I'm going to write it as a star here, is that all half reactions are already balanced. So I won't have to balance the half reactions individually anymore. I can go right to the step when I'm combining the two of these reactions together. I could go right to the step of finding a lowest common multiple and just balancing the full redox reaction. Now, something else I want us to understand as well. If we know that the left-hand side, so this whole side over here, refers to reduction reactions, that means that all the starting materials here, so F2, PbO2 solid, SO4 2 minus, MnO4 minus, ClO4 minus at H plus, all of these on the left side are the OAs. And by the same token, on the other side, and we'll use a pig for this here. On the other side, so your F minus, your Ag solid, your H2O2, all of these are reducing agents. So OAs are on the left side and RAs are on the right side. And so once again, if we're reading our booklet from left to right, we're dealing with a reduction reaction, and any of the entities that are on the left side are oxidizing agents, or OAs. And if we're reading the reaction from right to left, we're looking at an oxidation reaction. And any of the starting elements on that side, or compounds, are reducing agents. Now, another thing that I want us to understand is that this table is organized in a very particular way. The first compound or molecule that you see over here, fluoride gas, this is actually the strongest oxidizing agent, period, out of all the oxidizing agents that we have at this table. And what that means is it has the greatest attraction to its electrons. So not only is it going to hold its own electrons very well, but it'll also try and attract the electrons of others, which is why it's the best oxidizing agent, which means ultimately that it's going to get reduced before anything else on this table. Now, as we go down this table, your OAs get weaker, which means that, they attract electrons less and less. So the strongest at the top and the weakest would be at the bottom. Now, in contrast to that, we're going to focus on the right side of the table and look at something like lithium solid. Lithium solid has the weakest attraction to its electrons, but what that does is it's going to make it the strongest reducing agent, which means it'll most willingly, and I'll draw a little arrow here, we'll write it a different color, it's going to most willingly lose electrons, which is going to make it the strongest reducing agent. So the strongest reducing agents, in contrast to the oxidizing agents, are actually at the bottom, and they actually get weaker as we go up. So as we go up here, weaker RAs, to the point where the weakest RA is the F minus ion. So this is the weakest RA, so it works at opposites. The top left side of the table is the SOA, and the bottom right side of the table is the SRA. Now, what does this have to do with spontaneity? Well, I want you to look all the way to the farthest right side of the table and see something called the electric potential voltage. What this really is this is electrical potential energy. So I'll just write electric potential E. And so it's essentially energy. And each half reaction whether it's getting reduced or oxidized, whether it's an oxidizing agent or a reducing agent, is associated with a certain type of energy. And we categorize electric potential with the unit of volts. And so whenever one of these combine, let's say this and this, you're going to have a set difference in volts or a change in energy. And based on the value of that change in energy, we can determine if the system is going to be spontaneous or not, or if the reaction is going to work. So the general rule is this, and how we're going to use that table to guide us, is that in a redox reaction, if the SOA is above the SRA, the reaction is spontaneous, meaning it's going to work, at least from the electric potential side. And what we mean by above is literally above. Like you see how this diagram shows us SOA is above the SRA. It kind of makes a slant that looks like that. That would be a spontaneous reaction. I'm going to go to the table right now and show you what we mean. So let's say our two reactants are fluoride gas, and we'll highlight this with another color, and mercury liquid. Your fluoride gas is the SOA, and your mercury is the SRA. And looking at this table, we could see that the SOA is literally above your SRA, so this would be spontaneous. So this reaction would definitely work in a real-world setting. But let's see how that would look like if we used other elements. So let's say we're going to mix chlorine gas and iron 2+. Well, chloride gas over here, in retrospect, would be the SOA. And when we say SOA, we're talking about the strongest oxidizing agent in the reaction that you're talking about. So this is the SOA, and this is the SRA. And we can see that even in this, the SOA is literally above the SRA. So this too would be spontaneous, meaning that it would work. Now, let's look at another reaction though. Let's say we told you that water is going to mix with iodide solid. So water on this side is the SRA because there is no other reducing agent. This one is the SOA. Now when we draw the line for them to meet here, we would actually see that the SRA is physically above the SOA. So this would be non-spontaneous. And so this reaction wouldn't work at all. And in fact, you would see that if you mix iodine solid with water, nothing would really happen. And we're going to show you that when you guys get back to class. So here's the 5-step method for predicting redox reactions, because a lot of the times we're going to have solutions, which means that there's more than one ion or one solid going on at a time. And so how do we deal with more complicated redox reactions than the ones that we were briefly mentioning previously? So the first thing you're going to do is list all entities present and classify each as a possible oxidizing agent, reducing agent, or both. Do not label spectator ions. I'm going to comment on this one for a second here. If it's a strong acid, so strong acid, remember, is the first 6 in your data booklet on page 8 and 9. If it's a strong acid or ionic, and I'll write that in a different color here, or ionic, believe it or not, that says ionic. Hold on, my N is really bad. Strong acid or ionic, you're going to split into ions. So we're going to write for strong acid or iodic, always split into ions. So what we mean by that is, for example, and I'll just write it at the bottom here, so example, if you have HCl, HCl is a strong acid, so instead of writing HCl when you list the entities, you're going to go H plus and Cl minus. Okay, at the same time, let's say I have an ionic compound like NaCl. I'm going to go Na plus and Cl minus. I won't just list NaCl. But remember, this only works, okay, if it's iodic or if it's a strong acid. Then we're going to label the strongest oxidizing agent, right? So that would be our SOA. That would be from the table. Oops. And then, right, and then we're going to write the equation for its reduction. This is from the table, so I don't want you making up your own reactions. They're already balanced for you, okay? So this is from the table. Then we're going to pick the strongest reducing agent, which is the SRA. Okay, believe it or not, that is an R. I don't know what's going on, sorry. Okay. Yeah, that's still it. My God, what is going on with my R's? Okay, and same thing. The half reaction is going to be from the table, so don't make up your own. Then we're going to, it says balance the number of electrons lost and gained in the half reaction equations by multiplying one or both equations by a number. Then add the two balanced reactions together. This is just balancing full, so you just balance the full redox, right? Like we have done previously. Okay, so balance full redox reaction. Okay. And when it says non-ionic equation, that just means cancel any like terms that are present. And then use the spontaneity rule. Predict whether the non-ionic equation represents a spontaneous or non-spontaneous reaction. And what you're going to see is, once you've identified the SOA and the SRA, is the SOA above the SRA? And if it is, it's spontaneous. If it's not, then it's non-spontaneous. Let's look at an example and see how this works.